next section here deals with resonance. Resonance is a big topic in organic chemistry, and it's something that just kind of keeps showing up really for the rest of the year from time to time. In some chapters, it's emphasized a lot more than others, but it's a topic that we really need to understand. So it occurs when there are several different possible arrangements of multiple bonds and lone pairs on a given skeleton for a given formula. So one thing to point out is in order to have these resonance structures, we need to have available p orbitals because it's the pi bonds essentially that are going to be moving. Now, in one of our previous lectures, we talked about carbon dioxide, and we talked about how it has different Lewis structures. And those Lewis structures differ based essentially on where our double bonds are going to be. So let's take a look over at this first structure, and we'll put in our lone pairs here. All right. Now, if we go through and calculate our formal charge here, it's 0 for oxygen, 0 for carbon, and 0 for the other oxygen there. Okay. Now, how do we get from this structure that's on the left, where I just put in all the lone pairs, to the structure that's in the middle here? Well, what we've done essentially is this, is we've taken a set of electrons, right? If we go through and put in our lone pairs down here, it would look like this. Let's see if we can track this flow here. But what we've done essentially is we've taken a set of electrons like this, and we've converted them into a multiple bond because we have a double bond here, and then this side's a triple bond. So what we're going to do is we're going to take those electrons and we're going to draw them out like an additional bond, a triple bond there. And to show that, we're going to start off here, and we're going to point to where those electrons are going to go. So that's where they moved to, right there. Now, obviously, we didn't leave it like that, right? If we leave it like that, it would have this many bonds on our carbon, and that's not good. So instead, what happened is one of these set of electrons, it's in the p, the pi bond here, the pi bond, is going to come over and turn into a lone pair. So we're going to start off, and we're going to draw an arrow here and point around to where they're going to go. Now, it doesn't matter specifically where on the atom, so we usually just point to oxygen. So that would be our first kind of electron flow. Right? That gives us our intermediate structure here. All right, now, going from this middle structure, the one that's in the middle, to the one that's on the right, if we put in our lone pair here, we have 3 lone pairs at the end and 1 at the other end. So remember, when we calculate formal charge for this oxygen down here at the end, for example, like this guy, it's equal to the number of electrons that it wants minus how many it owns. So it has 2, 4, 6 is a lone pair, and 1 from the single bond, that's 7. So it gives you a minus 1. Down here, we know the formal charge is a plus 1 there because, again, it wants 6. So right now it has 1, 2, and then 3, 4, 5 around it. So we know that it has 1 lone pair. All right, but going from this intermediate middle structure here to the structure on the right-hand side, what we need to do is we need to come around and we need to do another electron flow essentially here, right? So essentially what we're doing is we're taking some electrons here at the end and we're moving them over to this position. So 2 lone pair here have been converted into another bond. You get a triple bond right here, right? And then 2 of our triple bonds are going to be converted to lone pairs. It's kind of the idea there. Now, we're going to practice putting arrows in like that as we go through some more of these structures. So let's hold off on the arrows in the last step here before we get all of the nuances down here, guys. So let's look down below. There's some important points here. So neither structure can be called more correct. They are all valid for the molecule, right? So all of them are. So they are all valid, right? Not just 2. So there's 3 there. Okay, now one might be a greater contributor. Okay, so the greater contributor is the one that has no formal charge. So carbon dioxide spends most of its life living like the structure that's on the far left. But the other two structures exist. A couple of other additional points here that are important to point out. First, none are completely correct. Okay. Now, the second thing that I want to point out here is that the actual molecule is a hybrid of the individual structures. Right? It's a weighted average. Remember, we said that first structure up here at the top perhaps contributed more because of its formal charge. We'll talk about that a little bit more in just a second. The other thing is that the structures are not in equilibrium with each other. So just a little note here, we don't use this type of arrow. Those are equilibrium arrows. So we're not going to use that. What we want to use is resonance arrows, which is this. Okay. And then the other thing is that the skeleton does not change between resonance structures. So this structure that's this intermediate middle structure right here is different from this structure. Even though if you built the model, you could rotate them and they would overlap with each other. They'd be superimposable. We can't do that with resonance. We have to imagine that we nail each of the atoms down and that every oxygen, for example, is a little different. So you have maybe like an oxygen A and an oxygen B. So then the rotation wouldn't work anyway. And again, the only thing that changes or moves here between resonance structures is the multiple bonds and lone pairs. That's the only thing that we can do. So let's take a look here at how we move electrons in these resonance structures. So this is called curved arrow notation, and it's something that we're going to be using when we look at mechanisms as we go throughout the whole year of organic chemistry. So not only does it show up in resonance, but it's an important concept to understand because it just shows up so frequently in the organic reactions that we're going to learn. So we use curved arrow notation to represent the movement of electrons in these Lewis structures. Now there's two types of curved arrows, right? The first one is just your regular double arrow. And for that double arrow, it shows the movement of two electrons. So you have 1, 2. It's a lone pair, or it could be a double bond, a pi bond there. So what we do is we start off where they are and we come around here and we use a full arrowhead like this. Okay, so it just, again, it shows two electrons moving, right? Now, the tail starts at the electrons that are moving and the head shows where they're going to go. So for us, this is probably going to be about like, I don't know, maybe 98% of the time. All right, the other 2-ish or so percent is going to be when we see a single electron moving. And these are called radicals. So a single electron, again, we start off where it is, and we use a fish hook arrow here. So it's like half of an arrowhead. Okay, so what we want to do is we want to figure out both of them. But again, the stuff on the left-hand side, that's what we're predominantly going to be seeing as we go through and look at mechanisms and stuff. So if we look down below and we want to compare resonance forms, we can use the following criteria, beginning with the most important, generally speaking. So first, we want to have as many octets as possible. We want to have as many bonds as possible. We want to have as little charge separation as possible. So we're watching out for formal charges, for example. And generally, we want negative charges on the more electronegative atoms. So let's look at these criteria as we go through and see if we can practice drawing some resonance structures here together. So there are 5 basic things that you're going to be looking for here to spot resonance. So let's take a look at the first one. It says, look for an electron deficient atom next to a lone pair bearing atom. All right, so let's build this. So here's an atom. Let's make it with 3 bonds. So this is electron deficient, right? Formal charge is a +1 if there's 3 bonds to it. And then let's put it next to a lone pair bearing atom. So what about an OH, like of an alcohol. All right, so this is an example. So we have a lone pair bearing atom, oxygen, adjacent to an electron deficient atom. So what we want to do is we want to take one of these lone pairs here, and we want to convert them into double bond. And we don't circle them like this when we draw them out. I'm just trying to highlight it. It doesn't matter which one you take either. Now we're going to swing around and we're going to do this full arrowhead here. Now we're going to use our resonance arrow. So the full arrowhead on both ends here. And what that's going to give us is the following molecule. It gives us this. Now let's see if we can figure out formal charges. So formal charge on carbon here is now 0, but oxygen is a positive. Right? It has 3 bonds to it in a lone pair. Kind of like H3O+, has 3 bonds in a lone pair. So let's talk about which one's the greater contributor. Well, is it better to have an incomplete octet or a full octet? Well, the structure on the right has a full octet. So this structure here will be our major. Again, because we have a full octet here. And that's it. So there's no other resonance structures, because remember, it's only lone pairs and pi bonds essentially that can move, right? Or radicals, if we're including those in here too. All right, so let's look at another one. So number 2, we're going to look for an electron deficient atom adjacent to a pi bond. All right, so let's build that. So let's make these a CH2 here, a double bond here. Let's make that a CH3. And then over here, let's make that a CH2. All right, now we're starting off with this. That again, that carbon with 3 bonds is where that plus charge is going to be. And let's see if we have satisfied this rule number 2 here, or what we're looking for. Electron deficient atom, that's your carbon here, adjacent to a pi bond. All right, pi bond. So remember, this is your pi bond, right? Here. All right, so let's talk about how to put our arrows in here. So in this case, what we want to do is we want to take this set of electrons, and we want to swing over here, and we want to convert them into a pi bond over on this side. Right? So when we do that, we're going to get CH2, carbon, CH2, CH3. Remember, the skeleton can't change, so we're stuck with this. We're putting that double bond over here, and then that leaves behind a positive charge on the other atom. Now, these are both the same energy. They both have incomplete octets. There's not one that's better. So we're just going to say these have the same energy. Okay, so let's look at the next one here. So the next one is to look for a lone pair adjacent to a pi bond. Okay, so lone pair adjacent to a pi bond. Well, let's build a molecule that has this. So here's a pi bond. All right, now we're going to be adjacent to the pi bond. And then over here, let's put a lone pair. So the formal charge on that carbon is a minus. So again, here's your lone pair adjacent to a pi bond. Now we're going to draw a resonance structure of this. And we're going to do this here, put our resonance arrow in. And then we're going to take this lone pair and we're going to convert that into a double bond. So lone pair to double bond to lone pair. So this one has a pattern too. So lone pair goes to a double bond, and then double bond goes to lone pair. That typically is the pattern when we see a negative charge. So what we're going to get in the end here is CH3, CH2. Oh, remember the skeleton doesn't change. But now that's going to be a double bond. And then we're going to have an extra lone pair on the oxygen and a minus charge here. So that when we look at this, which one is better here? Well, they both have full octets, so that's good. The structure that's on the right has a negative charge on the more electronegative atom. So probably this guy over here is going to be our major of the two. Now remember, it doesn't mean that's the actual Lewis structure. It just means that in the hybrid, because it's a weighted average of both of these, right, essentially, that the structure on the right contributes more. And those are the big ones, 1, 2, and 3. 4 is fairly straightforward. So it deals with something called aromatic rings. So aromatic rings are special. They get 2 chapters, chapter 16 and chapter 17 in our Wade textbook. So what we're going to do here is we're going to push multiple bonds, and I don't know why that happened, but these are pi bonds into adjacent multiple bonds. And again, that's a pi bond around a ring. So kind of the one that you guys have probably seen maybe in general chemistry, sometimes they'll draw this out if you get to like the little organic section at the end, is something that looks like that. And of course, there's H's all around this molecule. And this is known as benzene. Okay. Now, line structure wise, typically we would draw that out like this. But these electrons are all kind of in resonance with each other. So we could do this. We could take this and we can move it over to right here. And then we have to move this one. It's kind of like these dominoes kind of keep falling over and affecting the atom that's next to us. So it's a domino effect there. So that would be the same as drawing this out. And again, we put in our resonance arrow here. And then we put our double bonds here, here, and here. And that would be the other resonance structure of this. Now, those electrons, just as a side note, they move around very quickly. These both have the same energy. So sometimes, guys, you will see benzene written with this circle in the middle of it. And that just means that those electrons are moving around really fast. Okay, so 1, 2, and 3, and 4, that's what we see most of the time, but we do need to take a look at the radical involved in resonance. So let's look at this. So let's put a CH2 here, a carbon, an H, a double bond, and a CH2 up here at the top, and then a single electron right here. Well, it turns out that that carbon has no formal charge because it has 4 electrons around it. Now, we're looking for a radical, so here is our radical here, guys. That's your radical next to a pi bond, and that is your pi bond. Now, the thing that makes this a little bit complicated is that when we use arrows for a radical, we use these fish hook things. Okay? So what we're going to see is more arrows when we draw these structures out. So basically what's going to happen is this, is we would like to form a new pi bond right here. We want a new pi bond. Now, pi bond is made up of 2 electrons. We only have 1 here, so we're going to go ahead and contribute that electron to here. That's half of our pi bond, and we're going to get the other half from the pi bond that's adjacent to us. So we're going to steal one of these electrons, and we're going to put it right there. That leaves you with 1 more electron up here that then comes up to this position. All right, so again, more arrows on this. You kind of get used to it over time. But that would give you this is your other resonance structure. And these have the same energy. So again, 2 resonance structures here for this with equal energies.